The table shows information about some of the elements in the third period. Complete the table to show the maximum oxidation number for each element in its compounds. Sodium's been done, and chlorine. We know sodium is in group 1, so 1 electron in its outer shell, so it can lose 1 maximum to form an ion with a 1 plus charge, or an oxidation number of +1. Magnesium can lose 2 electrons, so the maximum oxidation number for magnesium will be +2. Aluminium can lose 3, therefore +3. Phosphorus in group 5 or 15, so it can lose 5 electrons, that would be +5, and sulfur +6. Explain why the atomic radius of elements in the third period decreases from sodium to chlorine. So you need to consider the factors influencing the size of an atom. So we have discussed the fact that we need to consider the number of electron shells. If we have only 1 electron shell versus 1, 2 or 3, obviously the more electron shells we have, the bigger an atom will become, or we'll see an increase in atomic radius. But if we have the same number of electron shells, we need to consider the size of the positive charge in the nucleus, the nuclear charge. Because if the distance and the shielding is the same, the size of that nuclear charge will have the biggest effect on the size of an atom. So to answer this question, explain why the atomic radius of the elements in the third period decreases from sodium to chlorine. So as we go across the period from left to right, there's more protons, therefore the nuclear charge increases. We find the electrons in the same shell, so therefore they have the same amount of shielding, and as a result of that there will be a greater or stronger attraction between the nucleus and the outer electrons as we move from sodium to chlorine. The radius of the most common ion of magnesium is much smaller than the radius of the most common ion of sulfur. Identify both ions and explain the difference in their radii. So we know magnesium will lose 2 electrons to form an ion with a charge of 2 plus, while sulfur, having 6 valence electrons, will gain 2 more electrons to form an anion with a charge of 2 minus. So how do we explain the difference in size? So we know that magnesium loses its outermost electrons, so it loses all the electrons in the outer energy level. Therefore the magnesium ion has 1 fewer electron shell than an ion of sulfur. Therefore it will be much smaller. On each of these following grids, you have to draw a clear sketch to show the variation in the stated properties. On this one, it will be the variation in the atomic radius of the element. And below each grid, briefly explain the variation you have described in your sketch. For each explanation, you should refer to the important factors that cause the differences in the property you are describing. So for this first one, the atomic radius of the elements going across period 3 from sodium to chlorine, we know that there's going to be a decrease in the size of the atoms, or decrease in the atomic radius going from sodium to chlorine. To explain this trend, we have to consider the 2 factors, the nuclear charge and also where we add the electrons, or where we find the outer shell electrons. Because all of these elements are in the same periods, the electrons are added to the same shell, and as we go from sodium to argon, there is an increase in the nuclear charge. Therefore, as a result of the stronger attraction between nucleus and the outer shell electrons, we're going to see a decrease in the atomic radius going from sodium through to chlorine. For the trend in the melting points, we know that we have an increase in the melting points as we go through the metals from sodium to magnesium to aluminium, because you have stronger metallic bonds in aluminium compared to magnesium, and again stronger in magnesium compared to sodium. Silicon will have an even higher melting point than aluminium because of the giant molecular structure and the strong covalent bonds between that large number of silicon atoms. So you can have an increasing trend from sodium going up to silicon. And then we drop down to phosphorus and sulfur and chlorine because they've only got simple molecular structures with weak van der Waals forces between the molecules. So your trend will then go down to phosphorus. Phosphorus will have a lower melting point than sulfur because sulfur molecules contain more electrons than the phosphorus molecules. And then it drops down again to chlorine, which will have the lowest melting point of those non-metals. So if we explain that quickly again, what would you write down for your 3 marks here? So sodium and aluminium and magnesium all have metallic bonding. Silicon is giant molecular, and then phosphorus, sulfur, and chlorine are all simple molecular structures. For electrical conductivity, we know that the metals sodium and magnesium and aluminium are all good conductors of electricity with an increasing trend from sodium to magnesium to aluminium. And then we're just going to drop down sharply to silicon, which is only a semiconductor. And then phosphorus, sulfur, and chlorine, we know are electrical insulators, so they won't conduct at all. So the trend will be an increase from sodium through magnesium to aluminium, and then we drop to the semiconductor silicon, and then it drops to 0 for phosphorus, sulfur, and chlorine. So for your marking points, you're going to have to state that sodium, magnesium, and aluminium have increasing number of outer shell electrons to explain that increasing trend. Silicon is a semiconductor, and phosphorus, sulfur, and chlorine are covalent or simple molecular structures with no free electrons, therefore they cannot conduct. The table below refers to the element sodium to sulfur and is incomplete. Complete the melting point row by using only the words high or low. So sodium, even though it's a metal, it's got only a charge of +1 on the cations in that metal structure, and each atom will only contribute 1 electron to the sea of delocalized electrons. So the weakest of the metallic bonds in period 3, so it's actually a metal with quite a low melting point. For sodium, they will write in low. Aluminium, stronger metallic bonding than magnesium, so that will be high. Silicon is even higher, so also high. And then we get to phosphorus and sulfur with simple molecular structures, therefore low and low melting points. Complete the conductivity row by using only the words high, moderate, or low. Sodium, a metal, so the electrical conductivity high. Magnesium high. Aluminium high. Silicon, the semiconductor, so we will put moderate. And then the simple molecular structures, phosphorus and sulfur, will have low and low for electrical conductivity. On the axis, sketch the trend in melting point of the element sodium to sulfur. So this is a repeat of one of the previous questions, so try to answer this one individually and try to put down some detailed statements to explain your sketch. We know that as we go through the metals from sodium, magnesium, aluminium, who have increase in the melting points, silicon will have the highest in that period, and then it drops down sharply to phosphorus, but sulfur will have a slightly higher melting point again. We'll explain that, the reasons for that, in a minute. So you need to have an increasing trend to silicon, drop to phosphorus, and then you can have a slight increase up to sulfur again. So your 3 statements to explain your sketch. So first of all, let's start with the 3 metals. So there's an increasing strength of metallic bond from sodium to magnesium to aluminium, or you can state that as a stronger attraction between the delocalized electrons and the positive ion. So the melting point of sodium is lower than magnesium, and magnesium is lower than aluminium. Moving on to silicon, It is a giant covalent structure, so it has the highest melting point due to the breaking of the strong covalent bonds between silicon atoms. Or you can state that a silicon requiring more energy because the covalent bonds in silicon are stronger than metallic bonds. And then moving down to phosphorus and sulfur, they only have weaker intermolecular forces or van der Waals forces, which are weaker than the covalent and the metallic bonds, so they have lower melting points. And then lastly, just to explain that increase again from phosphorus to sulfur is because S8 or the sulfur molecules have stronger intermolecular forces or van der Waals forces due to the higher number of electrons in those molecules. Therefore, the melting point of sulfur is higher than that of phosphorus. So any of those 4 points, you can put down as your 3 statements. Argon, Ca2+, and K+ contain the same number of electrons. In other words, they are isoelectronic. They've got the same electron configuration. So we find all the electrons in the same shell. In which order do their radii increase? So the only difference between these will be the number of protons in the nucleus, okay, or the nuclear charge. And if we look at the periodic table, argon's got 18 protons, potassium 19, and calcium 20. So the charge in the nucleus will be 18 plus, 19 plus, and 20 plus. So the one with the highest nuclear charge will have the strongest attraction for the outer electrons. Therefore, that outer shell will be pulled closer to the nucleus, giving it the smallest atom, or this ionic radii. They will be the smallest. So the smallest one will be calcium. Then we move to potassium, K plus, with 19 protons, and therefore a charge of 19 plus in the nucleus. And then the last one will be argon with the largest radius. So the correct answer there is C. The use of the data booklet is relevant to this question. Why is the ionic radius of a sulfide ion larger than the ionic radius of a potassium ion? So we're looking at sulfide ion, which is S2 minus, and then the radius of a potassium ion, which is K plus. Okay, so both of these ions will contain the same number of electrons. So sulfur will gain 2 electrons to get to 18 electrons. A potassium atom had 19 electrons initially, but then lost 1 to form a K plus ion. So we'll also have 18 electrons. So these structures will have the same number of electrons. So the difference will once again be the charge in the nucleus. So if we compare sulfur with potassium will have a greater nuclear charge. Let's just look at the options. Ionic radius always decreases with increasing atomic number. Okay, so that's not true. It is true for cations and then also true for anions, but it depends on whether you're looking at the individual charges or not. So we can't just apply that as a rule, because as we go from cations to anions, we see a definite increase in the ionic radii. So not A. Positive ions have smaller radii than negative ions. Yeah, so generally, as a rule of thumb, that will be true, because positive ions will lose their valence electrons, lose their outer shell, while negative ions will gain. But it will also depend on where in the periodic table we find these positive and negative ions. And then the potassium ion has more protons in its nucleus than the sulfide ion. Okay, so that's our correct answer in this case. We've got a much larger nuclear charge in the potassium ion compared to a sulfide ion. And then the last one, the sulfide ion is doubly charged. The potassium ion is singly charged. Okay, so that is not the reason either. The important thing is the charge in the nucleus, which attracts the outer electrons and not the overall charge on the ion. Which diagram correctly shows the atomic radii of the elements magnesium, aluminium, silicon, and phosphorus plotted against their melting points? So if we consider the atomic radius for each one of these elements, we know that as we go from left to right across period 3, there's a decrease in the atomic radius. So it should decrease from magnesium to aluminium to silicon to phosphorus. So let's look at option A. Phosphorus must have the smallest radius, followed by silicon, then aluminium, and then magnesium. Okay, so not A. If we look at B, okay, we can rule this one out. We start with aluminium with the smallest, which is not correct. If we look at C, we go from phosphorus to silicon to aluminium to magnesium. So that's a possibility. Phosphorus to silicon to aluminium to magnesium. Okay, so that's another possibility. So it could be C or D. In terms of the melting points, we know that magnesium to aluminium to silicon will show an increase in the melting points if we go from an increasing strength of metallic bond to the strongest giant covalent structure or giant molecular structure, and then it will drop down to phosphorus. So we're looking for C or D to show that trend in the melting point. So this one's got phosphorus as the lowest melting point. Yes, that is correct. And then it should be magnesium, also correct, and then aluminium and silicon, the highest melting point. So C, this stage, is the correct answer. Let's just see if we can rule out D as well. Phosphorus the lowest, then magnesium, correct, but then it should be aluminium and then silicon. So we can rule out D as well. So the correct answer for question 15 here is C. Elements J and K react together to form compound L. J and K are both in period 3. Element J has the smallest atomic radius in period 3. And there are only 2 elements in period 3 which have a lower melting point than element K. Which compound could be L? So you need to know your trends pretty well to answer this question. So let's look at the information. So J and K react together. So the fact that they react means that we can probably rule out any noble gases. So we can rule out argon, the far right of period 3. J has the smallest atomic radius in period 3. We know the trend across period 3 from left to right is a decrease in the atomic radius because of the increase in the nuclear charge. So the furthest one to the right with the smallest atomic radius is chlorine. So at this stage, we're only looking at option A and option D, where sulfur will be ruled out here. Then the next bit of important information, there are only 2 elements in period 3 which have a lower melting point than K. So we know we're looking at the simple molecular structure, so it could be either phosphorus, sulfur, chlorine, or argon. We know argon's got the lowest of the melting points. Chlorine's got the second lowest, so it's between phosphorus and sulfur. We know sulfur's got more electrons in the structure than phosphorus, so a slightly higher melting point. So the correct option there must be P for phosphorus. So the correct answer is option D. So not magnesium. So with its metallic bonding, it's actually got the third highest melting point. It's only magnesium. It's only aluminium and then silicon with higher melting points than magnesium. There's a description here or an introduction as to how they measure atomic radius, but I'll go straight into the question. The table below contains the resulting atomic radii for the elements of period 3 of the periodic table, sodium to chlorine. Explain qualitative this variation in atomic radius. And we can see the trend here. I'm sure you know the trend, but you can see a clear decrease in the atomic radius as we go across the period. So we know the factors to consider will be nuclear charge, and we know the nuclear charge increases from sodium to chlorine. The electrons are in the same shell and have the same amount of shielding. Therefore, the attraction between the nucleus and the outer electrons increases. Suggest why it is not possible to use the same type of measurement for argon. As we mentioned earlier, argon is a noble gas, so very unreactive or inert. Therefore, argon does not form any bonds or compounds. Or you can say that argon exists only as single atoms, or argon is monoatomic. Use a data booklet to complete the following table of radii of the cations and anions formed by some of the period 3 elements. So you would go to your data booklet on page 10. There's a table of atomic and ionic radii. So it is just a matter of copying down those values into this table. Explain the differences in size between the cations and the corresponding atoms. We know that cations form when atoms lose their valence electrons. So to explain the difference in the size between the cations and the corresponding atoms, you can state that the cations have lost their outer shell, therefore will have a smaller radius. You can also state that the cations contain fewer electrons than they do protons, therefore the nucleus has a greater attraction. Explain the differences in size between the anions and the corresponding atoms. So how do we explain the increase in the radius of an anion compared to the corresponding atom? We know that anions form when atoms gain electrons. So as a result of this increase in the number of electrons, there will be more repulsion between these electrons, and therefore the nucleus will have a smaller attraction.